Section 5.2 is titled Properties of Rational Functions. And so just like in section 5.1, we were going to be looking at looked at polynomial functions and some details on those and specifics on those. In section 5.2, we'll be looking at what are called rational functions and just looking at several different things involving those. You can see our objectives here. We'll talk about how to find the domain of a rational function. Also look at what are called vertical asymptotes of a rational function, also horizontal and oblique asymptotes. So some new words there, some things that you may not be familiar with, especially that word asymptote. So we'll get to that here pretty soon and see what that's all about. But first, let's define our rational function. Rational function, as far as the definition, is pretty simple. It says a rational function is a function of the form p of x over q of x. So we have this fraction, and these two functions, p of x and q of x, are polynomial functions. And q is not the zero polynomial. So some examples of what that looks like. Basically what we're doing is we're dividing two polynomials. So you can see these three examples. The numerator is a polynomial x squared minus 4 for this first example. The denominator is this trinomial x squared plus x plus 1, and so just dividing two polynomials. Okay, so we'll call those rational functions. Now when we want to look at the domain of a rational function, the way that we figure that out, it's actually a question we've answered before back in chapter 3 when we talked about domains of functions. If you'll recall, one thing we said about domains of functions is the denominators can't be 0. So if we have a rational function, like here 2x squared minus 4 over x plus 5, the restriction on this function, we're going to look at that denominator and say, okay, when is x plus 5 equal to 0? Well, if you solve that, pretty simple, subtract 5 from both sides, we get that if x equals negative 5, then that denominator is 0. So we can say the domain is x values such that x is not negative 5. Or remember, we can also use an interval from negative infinity to 5, and then also join that, negative 5. And then from negative 5 to positive infinity is the other way we can write that answer. So two ways to write that. Both are correct. Just pay attention in the homework. Make sure that you answer it in the way that the homework's asking. Next question, part B here, 1 over x squared minus 4. Again, we're just looking at the denominator here, x squared minus 4. Whoa. Set that equal to 0. And there's two ways we can solve this. The way I'm going to do it is by factoring. So I can factor that as a difference of squares. Make it x plus 2 times x minus 2. And then from there, set each factor equal to 0. And we get negative 2 and positive 2 as the two solutions to that equation, which means those are the two x values which caused this denominator to be 0. So we would say that the domain is x values such that x cannot be negative 2 or positive 2. So one way to write that. And actually, I think the way that the software would want that is to list that twice there. I'm going to go ahead and do that, like so. Or we could, again, use interval notation. This gets a little bit cumbersome with the interval notation here, but we'll put it up here anyways. Negative infinity to negative 2, and then from negative 2 to positive 2, and then from 2 to infinity. Basically just breaking that up, put a little gap in there at each x value that's not included. So again, either of these will work for your answer. Part C, x cubed over x squared plus 1. So if we look at x squared plus 1 again, really interested in that equation there, setting that equal to 0. If we try to factor that, it doesn't work. That's not a difference of squares. We do have a plus sign here. And so we can't factor that as a difference of squares. Really, we can't factor it at all. And so it's not factorable. Another method we have of solving an equation here where we just have the single squared term is to isolate that squared term. And then if we take a square root on both sides, well, what we end up with there is this piece right here. There's no real solution when we do a square root of a negative. And so what does that mean? If there's no real solution there, then there's no x values that cause this denominator to be 0. Think about it. If you square any number and add 1 to it, you're never going to get a 0. So the domain here is all real numbers. So we could say from negative to positive infinity would be the domain there. And part D, x squared minus 1 over x minus 1. This one is pretty simple. Just look at the denominator. Again, it's x minus 1. If we solve that, we get that x equals 1 is the x value that causes that denominator to be a 0. So again, the domain, could write it a couple of ways. X can't be positive 1, or again with the intervals, it's like so. Okay. Now let's look at this function here a little bit more in depth. X squared minus 1 over x minus 1. The next question here, this is just kind of something to make you think a little bit. Are these two the same function? Here's that function we just worked with, and here is f of x equals x plus 1. They look like they are not anything alike. You know, those don't appear to be the same, but the reason we're comparing these is if you take this r of x function, factor the numerator, difference of squares there, you can then cancel the x minus 1s, and you end up with r of x equals x plus 1. So does that mean these two are the same? We can reduce that fraction down to x plus 1, so those must be the same, right? The answer is they're not actually the same, so no. And the reason being is the domains are not the same. They have two different domains. For this function right here, x can't be 1. For this function, x can be 1. Okay, so you know, we can kind of prove that to ourselves. If those two functions are the same, for every x value they should give the same value. But r of 1 is 1 squared minus 1 over 1 minus 1, which is 0 over 0, or undefined. F of 1 is just 1 plus 1, which is 2. So you see those are not the same at all. Okay, r of 1 and f of 1 aren't the same, so those two functions, they are not the same. And again, it just goes back to the domains. Okay, just asking that question really just to illustrate that two functions might look the same, but you have to consider the domains also. They have to have the same domains if we're going to say they're the same function. Okay. Let's talk about the graphs of rational functions real quick. Here's the graph of the rational function 1 over x squared. That's what we're looking at here. And this looks pretty interesting here. 1 over x squared, we have this left-hand piece and this right-hand piece. And those two pieces are totally separate. They're totally disjoint from each other. There is a gap between these two. And really what's interesting about this shape of this graph, and we've seen something kind of like this with the reciprocal function back in section 3.4, but what's interesting about this graph is the behavior near this y-axis here. As this left side gets closer to the y-axis, it gets closer and closer and closer, but it never actually touches the y-axis. This gap right here just gets smaller and smaller, but it never actually closes together. Same thing for this right-hand piece. It gets closer and closer to the y-axis, but it never actually touches or crosses that. There's a small, tiny little gap between those two pieces. And just to kind of show you where we're going with that, the name for that is called an asymptote. So this y-axis is a vertical asymptote. That's what we would call that. And we also have the same sort of thing happening down here at the x-axis, where these left side and this right side, these two ends of the graph, are flattening out, and they're approaching the x-axis, but they never actually touch the x-axis. They never actually cross over the x-axis. They just get closer and closer and closer. It's kind of a weird thing. But again, we would call this also an asymptote. In this case, it would be a horizontal asymptote. Okay. So that's what an asymptote is. It's a line that the graph approaches but does not touch or cross, and we're going to talk about that a lot more here in just a second. But that's 1 over x squared, and you can kind of get a feel for why that behavior is there. Why don't we have a point on the x value 0 on this vertical axis right here somewhere? Well, if x is 0, what's 1 over 0 squared? It's undefined, right? So that's why we don't get a point right there. And as far as this horizontal asymptote, if you do 1 divided by 0 squared, or I'm sorry, if you do 1 divided by x squared, that's always a positive value. If you square that x value, it always becomes positive, and so you never get an x value where the result after you do 1 over x squared is negative. So you don't get any points below the x-axis. So that behavior does make sense as far as why it doesn't cross over those two lines there. Okay, let's kind of look at graphing again real quick. This is graph the rational function r of x equals 1 over x minus 2 squared plus 1. And so the base graph we're using for this is, is 1 over x squared. And so what we've done is we've taken 1 over x squared, we've subtracted 2 from the x, and then put a plus 1 outside of that fraction. So 1 over x squared typically is this shape right here. That's that graph we just looked at. Okay, this is 1 over x squared. Remember, we have these asymptotes at those axes. Okay, so what happens when we do a plus 1 to our base function? That's a vertical shift up, right? So it's going to go up 1. So what that's going to do is it's going to actually move that horizontal asymptote up 1. And if we do minus 2 there inside where that x is, that's a horizontal shift to the right 2. So that's actually going to put this is at positive 1 and positive 2. That's where those are crossing now. So it's just a shift up 1 and to the right 2, and that basically makes our two pieces now fit in like this. Okay, so that's what our new graph is going to look like. Again, that's a sketch. Obviously, it's, you know, if you were to graph that, it would look better. And just for sake of seeing it, let's go ahead and do that real quick. I'm just going to punch both of these in. The first one's 1 over x squared. The other is 1 over x minus 2 squared. Oops. I'm just going to start over here. Having some problems. X minus 2 squared plus 1. So let's get our windows set back up here. And let me just zoom in where the interesting things are happening, which is kind of right in here. Okay, so there's the original graph, and then our new graph is shifted up 1 and to the right 2. So you can see that. It's basically what we expected to happen. Perfect.